Welcome to the deep dive. This is where we take a whole stack of information, pull out the really crucial bits of knowledge, the insights, and, well, give you a shortcut to being genuinely well informed.
That's the goal.
Today, we're diving headfirst into something that, okay, might sound a bit technical, but trust me, if you're building software, especially software you want to last, this is essential stuff. Software architecture metrics.
Absolutely crucial.
And we've been digging into this fantastic resource, Software Architecture Metrics, case studies to improve the quality of your architecture. It's got a whole team behind it. Christian Ciceri, Dave Farley, Neil Ford, just a powerhouse group.
Yeah, a really impressive lineup. Andrew Harmelaw, Michael Keeling, Kroll Lilienthal, Joan Rosa, Alexander von Zitzewitz, Renee Weiss, Dielson Woods.
Yep.
They all contributed.
Exactly. So our mission today, to unpack how measuring your architecture isn't just, about numbers. It's about getting real insights.
Making better decisions.
Right. And ultimately, building better systems that actually stick around. Get ready for, I think, some surprising facts and maybe a few aha moments that could change how you think about developing software.
Looking forward to it.
So let's unpack this. The core challenge, we see it everywhere, right? Software systems, they just grow complex over time.
They really do. It sneaks up on you.
It's like building a house, maybe adding rooms, another floor, but never checking the foundations.
Yeah.
And this leads to, well, something we all kind of dread, technical debt. Where did that idea even come from? Why is it such a headache?
That's a great starting point. The term technical debt,
Yeah.
it was coined way back 1992 by Ward Cunningham. Super insightful idea.
Okay.
He described it as basically what happens when you make wrong or maybe just suboptimal technical decisions. Could be conscious, could be unconscious.
So sometimes you're doing it, like for speed.
Exactly. Sometimes you choose to take on that debt, maybe to hit a deadline. But the catch is, just like a financial loan, those decisions, they mean extra, often expensive, work later. It's like paying interest.
Right, that makes sense. So whether it's deliberate or it just creeps in, what happens if you don't, pay it back? What are the long-term consequences?
Well, if you don't keep chipping away at that debt, you get what Corolla Lilienthal calls architectural erosion. It's a vivid term.
Erosion, yeah.
Think of that house again. A leaky faucet here, maybe a cracked tile there. Small things at first.
Mm-hmm.
But ignore them. Pretty soon you've got serious problems, a flooded basement. Maybe the foundation crumbles. That's architectural erosion. It makes maintenance, making changes. It gets more and more painful, more costly.
And slows down new features, right?
Absolutely.
Yeah.
It grinds feature implementation to a halt. Nobody wants to get stuck where every tiny adjustment costs a fortune and takes forever. It's a nightmare for teams, for budgets, everyone.
Okay, so it's a pervasive problem. What's the fix? Because it feels like gut instinct isn't enough here. We need something more objective.
Precisely. And Alexander von Zitzewitz points out this kind of paradox. Almost every other industry that makes complex things uses metrics for quality. Cars, planes, you name it.
But not always software.
Software often lags behind, yeah. The key insight is that objective measurement gives you that vital feedback loop.
Yeah.
It lets you see the quality, the maintainability.
Because it's not just about the system itself.
No, it directly boosts developer productivity too. Code becomes easier to read, understand, change. It makes the invisible visible. You get concrete data.
And a really practical tool for assessing this debt, highlighted by Corolla Lilienthal, is the Modularity Maturity Index, the MMI.
Ah, yes, the MMI. Very useful.
What's really insightful there, I think, isn't just the score itself, but the fact that it gives you this objective, data-driven argument. You can use it to say, okay, we need to invest in refactoring this system,
Or conversely, look, this one's maybe too far gone. Let's plan for a replacement.
Exactly. It cuts through the gut feelings, the endless debates. It gives you a roadmap for where to put your resources. Huge win.
And it's built on solid principles. Modularity is the biggest factor, about 45% influence. Are the code proportions balanced in the modules? Things like that.
Okay.
Then there's hierarchy. 30%, does the system have clear structures? Are there problematic cycles where things depend on each other in loops?
Right, avoiding those tangles.
And finally, pattern consistency, around 25%. How well are design patterns used? Are the relationships clear and maintained?
And the scoring gives you a clear picture.
It does. An MMI score of 8 to 10, low debt, you're looking good.
Nice.
4 to 8 means there's definitely some debt. Refactoring is needed to stop that erosion getting worse.
And below 4?
Below 4. That's high debt territory. You really have to seriously consider if replacement is the smarter long-term play, rather than just pouring good money after bad.
So these metrics, like the MMI, they seem incredibly powerful. Why aren't they just everywhere? Why isn't everyone using them?
It's that paradox Alexander von Zitzewitz talks about. Again, often it's simply a knowledge gap. Developers, architects, they might not know which metrics to use or how to interpret them.
Or maybe the tools are hard to find or use.
That too. The tooling can sometimes be a bit niche or not widely known, but that's exactly what this deep dive is for, to bridge that gap for you, give you practical insights, and sort of demystify using data in your architecture decisions.
Okay, great context. So let's zero in on some specific tools. The book really champions what they call the 4 key metrics. These come up in chapter 1. Folks like Dave Farley talk about them a lot.
The DORA metrics, yes.
Right. Deployment frequency, lead time for changes, change failure rate, and time to restore service. If you want to understand your software's health, these seem pretty foundational.
They absolutely are. You really can't overstate their significance. They often come straight out of your CI/CD pipelines.
Okay.
And they give you this direct, high-level view of your development performance. The first two, deployment frequency and lead time, they tell you about your development throughput.
How fast you can get stuff out, basically.
Yeah, how quickly and how often you can ship changes to production. And the other two, change failure rate and time to restore, they indicate your service stability.
How reliable things are once they're out there.
Exactly. How reliable is the system with those changes? And critically, how fast can you fix things when they inevitably break?
And the key insight here, it seems, isn't just looking at them individually, but together. You can't just push for speed and ignore stability or vice versa.
Precisely. That's the profound part. Optimizing one at the expense of the others, it just doesn't lead to sustainable benefits. It creates imbalance.
So if you deploy super fast, but everything breaks.
You're not actually delivering value, you're just delivering problems faster. These metrics force you to see the whole pipeline, the whole system. Real improvement comes from optimizing the entire flow idea to reliable production. You need all 4.
Okay, so how do you actually apply them? The book talks about needing some mental refactoring.
Yeah, you need to adapt how you collect the data based on your specific setup. Maybe you have a simple monorepo, or maybe lots of microservice pipelines.
Or complex multi-stage pipelines.
Right. Could be sub-pipelines, fan-in pipelines. The core idea is the same, though. Find the right points to grab the data.
So practically, where does that data come from? The instrumentation points.
For lead time and deployment frequency, you're typically looking at timestamps. The commit timestamp, the deployment timestamp. Your pipeline tools usually log these.
Okay, that seems straightforward. What about stability?
For change failure rate and time to restore, you need data on when a service degradation is detected and then when it's marked as resolved.
And failure in production.
Yeah.
How do you define that? It's not just cosmetic bugs, right?
Good question. No, it's generally anything stopping users from completing their tasks. Could be a broken feature, could be a major performance issue. It does require some judgment calls.
But you need to be honest about it.
Absolutely. Honesty and consistency in how you define failure are key for the team to trust the metric.
What if you don't have all this automated yet? Is it a non-starter?
Not at all. The book makes a good point here. Manual data capture is perfectly fine to start with. It's a stepping stone.
Automation is the goal, though.
Ideally, yes.
Uh-huh.
But what really matters, especially early on, is transparency. Be open about the data, how you calculate things, your definitions. That builds trust and gets the team engaged.
Okay, so beyond those foundational 4, there's this whole other toolkit of metrics for looking deeper, especially at maintainability. Alexander von Zitzewitz really digs into these.
He does. For instance, looking at coupling and structural erosion, there are metrics like average component dependency, ACD, and propagation cost, PC. These measure reachability.
Reachability, what does that mean exactly?
It's about how far the ripples spread when you change something. If you change one component, how many other components might be affected? High propagation cost
Means changing this one thing might force you to change lots of other things.
Bingo. It screams maintenance nightmare. Then you have cyclicity and relative cyclicity. These look for those circular dependencies.
Where A needs B, B needs C, and C needs A again.
Exactly. Those loops create really brittle systems, that ball of mud effect. Changing anything becomes risky. Smaller cycles are better, but ideally, you want none.
Okay, so we can spot these tangles, but how do you quantify the effort to fix them? That seems like the hard part.
Well, that's where the structural debt index, SDI, comes in. It's designed specifically to estimate the effort needed to break those cycles, focusing on the links to cut. It gives you a more concrete estimate for refactoring work.
Interesting. And there was another one, ML.
Right, the maintainability level, ML,
Yeah.
is described as somewhat experimental, but it tries to assess good design by looking for clear horizontal layering and vertical separation functional silos, basically aiming for non-cyclic dependencies. Higher ML suggests better maintainability.
Makes sense. What about just size and complexity? Are those still relevant?
Definitely. You have the straightforward ones. Lines of code per file, number of statements per method. Simple, but still useful context.
And then things like cyclomatic complexity. I've heard of that one.
Yeah, cyclomatic complexity measures the number of independent paths through code. Think of it like, how many different ways can this function run? The more branches, loops,
The
decisions.
higher the complexity.
Exactly. A high score, maybe over 24, often indicates code that's harder to understand, harder to test thoroughly, and frankly, more likely to contain bugs.
And indentation debt. That sounds oddly specific.
It might sound minor, but it's about deeply nested code. Layers upon layers of if statements or loops. Code like that becomes incredibly hard to read and reason about. You have to hold so much context in your head.
Okay, I can see that. And then there are metrics from version control, like Git history.
Yes. This is fascinating stuff, highlighted by authors like Adam Tornhill. Change history metrics. You look at number of changes, how often a file is modified, and code churn, how many lines are added or removed.
Why is that useful?
Because it helps you find hotspots. Files that change constantly, especially if they're also complex. Those are prime candidates for refactoring. The book even mentions visualizing this as a software city, where tall, dark buildings represent these problematic hotspots. It points you right to the decay.
Cool visualization. Any others worth mentioning quickly?
Sure. There's component rank, which is kind of like Google PageRank, but for your code's classes. It identifies central, highly connected classes.
High impact points.
Potentially, yeah. And lack of cohesion of methods, LCM4. That's a good one for spotting violations of the single responsibility principle. If a class's methods are working on totally separate bits of data,
It's probably doing too much. Needs splitting up.
precisely, it suggests the class should likely be broken down for better clarity and maintainability.
Wow, okay.
Right.
That's quite a toolkit. It's a lot to take in, but you can really see how these different metrics paint a picture, right? They're not just random numbers.
Not at all. They give you that objective lens into your software's health. They help you figure out exactly where to focus your energy for the biggest improvement.
So you have all this potential data. How do you make it usable? Christian Cesari and Dave Farley talk about moving towards dashboards.
Right. The ideal path is from maybe manual tracking at first to fully automated dashboards. Even starting small helps.
Yeah.
A minimal viable dashboard, an MVD.
What would that?
Maybe just the current values for a few key metrics, clear definitions of what they mean, and some historical data so you can see trends. That alone can be really powerful.
And who uses these?
Critically, they need to be accessible to the delivery teams. They're the ones who can act on the insights. Maybe rolled up read-only views for senior management too, for that strategic overview.
The book also flags this common problem, an anti-pattern they call the ownership shift, where DevOps becomes like a separate team just doing automation.
Yeah, that can be a real trap. It isolates the developers from deployment, from validation. It accidentally rebuilds the silos you were trying to break down.
Creates environment mismatches again.
Exactly. Becomes a blocker.
Yeah.
So how did teams cope if they're in that situation? Private builds become really important.
Yeah.
Running tests locally on your own machine before you commit anything to the shared code base. The idea is to catch defects before they even get into the main development line, the trunk.
Preventing problems entering the shared space.
Precisely. There's a case study, the unstable trunk one, that shows this well. A team used private builds, caught integration bugs much earlier, stabilized their trunk.
And help the QAs, too.
Big time. QAs could shift away from just reactively finding bugs that slip through towards more proactive stuff, functional validation, building test automation. It really changes their role for the better.
And for those situations, Christian Cesari suggests some specific process metrics.
Yeah, metrics focused on the workflow itself, like time to feedback. It's more qualitative, maybe indirect, but measures how long it takes, how much effort to get feedback on a feature.
Yeah.
Long times often point to process bottlenecks. Then there's inevitable integration issues. That's quantitative. A direct count of bugs that could have been caught earlier. High numbers often mean validations are happening too late.
And the last one.
Time spent restoring trunk stability per iteration. Another direct measure. How much time are developers spending fixing bugs that got checked into the main branch? It tells you how effective your prevention steps, like those private builds, really are.
The underlying message seems clear then.
It really is. That upfront effort to set up good private builds, it's way less costly in the long run than constantly fighting fires on the main branch, dealing with QA back and forth, managing all those bug tickets. It's proactive investment.
This leads to a really important question. How do you make these architectural ideas, these quality standards, sort of self-enforcing?
Yeah.
Neil Ford, Rebecca Parsons, Petra Kua, Renee Weiss, Arian Woods talk about architecture fitness functions.
Yes. Fitness functions are fascinating. They're not your standard functional tests checking if a feature works.
They're architectural tests.
Exactly. They check if the system stays within acceptable boundaries for those non-functional qualities. Performance, scalability, security, maintainability, whatever's important for that specific architecture.
Keeping the system fit for purpose.
Precisely. And Renee Weiss even maps this onto a fitness function testing pyramid, similar to the traditional test pyramid, but for architecture.
How does that look?
Bottom layer, fast, cheap atomic tests. Think static analysis, code coverage checks, run all the time. Middle layer, broader checks, maybe service level or integration tests for architectural rules. Top layer, more holistic, real-world tests, often running continuously. Monitoring production revenue, system reliability metrics, gives you that live pulse.
And the case studies really bring this to life. GitHub scientist tool using fidelity fitness functions.
That sounds powerful.
It really is. They could run old code and new experimental code side by side in production, but only for a tiny slice of traffic.
Comparing the results in real time. Yeah, comparing outcomes, performance, everything. But crucially, users only ever saw the output from the old proven code. It let them experiment aggressively, be truly agile, without taking huge risks with the user experience. A total game changer for safe innovation.
Wow. And the security example, the zero-day checks.
Another compelling one. Imagine having a dedicated security slot in every single deployment pipeline across your whole company, even for projects that aren't actively worked on.
Okay.
And in that slot, you have a fitness function that automatically checks for known vulnerabilities when something like the Equifax Struts vulnerability hits.
You could automatically scan everything, proactively.
Instantly, across the entire enterprise. It could find the holes before they're exploited.
Yeah.
It really shows how you can use automation and fitness functions to make your architectural rules stick, continuously validating quality, even against new threats.
So we have all these technical tools, metrics, fitness functions.
Yeah.
But how do you make sure the architecture itself is actually heading in the right direction, serving the business?
That's the crucial next layer.
Yeah.
Jerome Rosa and Renee Weiss really emphasize this. Architecture isn't static. It has to evolve as business needs change. It's a continuous journey.
Right.
And Anna's story from the Scaling and Organization chapter illustrates the risk perfectly. Her fintech company, Your FinFreedom, moved to microservices, but ended up with a distributed big ball of mud.
Ouch. So microservices didn't automatically solve the problem.
No, they just distributed the mess. It led to constant problems, frustrated, demotivated teams, a common pitfall.
So what did Anna do? How did they get intentional about it?
Her solution was smart. Connect the architecture directly to the company's mission and its key performance indicators, the KPIs, force intentional decisions
Wow.
through visual collaboration, specifically event storming.
I've heard of that. How does it help here?
Well, big picture event storming gets everyone in a room, support staff, developers, tax lawyers, whoever, mapping out the complex business processes visually together.
Like seeing the whole system.
Exactly. And that helps them spot where the implementation, the software architecture, has drifted away from how the business actually needs to work. That's how they saw the distributed big ball of mud wasn't really supporting the core process as well.
Okay, that finds the misalignment. What then?
Then you can use process modeling event storming to dive deeper into specific value streams, identify the hotspots, the waste, using lean ideas like the 8 wastes, waiting, defects, non-utilized talent, etc. And crucially, clarify the KPIs for that process.
And Joan Rosa has that interesting heuristic. Slower is faster.
Yes. It sounds counterintuitive, but investing that time up front to really deeply understand the KPIs, the business context, it pays off massively later. It stops you from making costly architectural mistakes, building the wrong thing or building the right thing the wrong way.
So metrics guide this intentional evolution.
Absolutely. You can use tools like a KPI value tree, connect those high-level business outcomes down to granular team goals, and then identify the leading and lagging indicators, the metrics that show if you're moving towards those goals.
And the door metrics fit in here again.
Perfectly. Deployment frequency, lead time, change failure rate, time to restore. They are powerful leading indicators for architectural change. They give you that fast feedback on whether your changes are having the intended effect.
And João Rosa adds other high-level ones, too.
Yeah, things that connect tech to the wider organization. Mean time to discover for IT incidents. Team throughput. Even employee net promoter score ENPS for team happiness and retention.
Linking architecture to employee engagement.
It shows how good architecture, enabling autonomy and reducing frustration, can make for happier, more productive teams. Anna's experiment proved it. She used deployment frequency and change failure rate to show that redefining domain boundaries actually improved both metrics for a key service, empowering the team.
Okay, this is great for intentional evolution, but what about those really tricky, hard to pin down problems, like measuring abstract technical debt or design maturity? That feels fuzzy.
It can feel fuzzy, yeah. And that's where Michael Keeling introduces the goal question metric GQM approach. It's a really elegant framework for tackling those gnarly, difficult-to-answer problems.
GQM, goal question metric. How does it work?
It's a simple three-step process. First, identify a clear goal. What do you want to achieve? And crucially, from whose perspective?
Okay, define the objective.
Second, brainstorm questions. How would you know if you're achieving that goal? What questions need answers?
Got it.
And third, define metrics. What specific, measurable things will answer those questions? You need precise definitions clearly linked back to the questions and the overall goal.
And the case study, the team that learned to see the future, that really shows GQM in action.
It's a fantastic illustration. This team had a major service outage. Bad news. But then, in the postmortem, they used GQM.
To figure out what they missed.
Exactly. They asked what metrics would have warned us before this happened. The GQM process helped them uncover architectural flaws, like they were only collecting certain data under heavy load, or it wasn't clear who was responsible for retries between services.
So it led to concrete changes.
Yes. They added things like a heartbeat component to monitor connections, adopted a fail-fast strategy for certain jobs, things directly addressing the gaps GQM revealed.
And the seeing the future part.
That was the real aha moment. 9 months later, a similar underlying issue started to occur again. But this time, the new metrics they'd put in place alerted them before any users noticed.
Wow.
What would have been another major outage became just a brief, internally managed inconvenience. It's such a powerful story of how GQM lets you turn those abstract worries into concrete, measurable models. It makes the future state of your system visible, actionable.
So wrapping this all up, what does it really mean for you listening? We've gone deep into software architecture metrics. We started with that subtle creep of technical debt.
The interest payments.
Right. And we've seen the power of targeted measurement, defining clear goals, asking the right questions, picking the right metrics, whether it's the big four key metrics or detailed coupling analysis or those high-level KPIs.
It really can transform how you build software.
It's not just tech for tech's sake, is it? It's about transparency, empowering your teams, making intentional data-driven decisions that actually connect back to business value.
Absolutely. The insights from all these authors, Cicero, Farley, Ford, Lilienthal, Keeling, all of them, they make it crystal clear, even when things aren't perfect organizationally.
Which they rarely are.
Right. Metrics give you that unbiased measure. They keep teams focused on shared, aligned goals, and that leads to faster delivery, lower costs, and ultimately much better quality software.
Okay, so here's my provocative thought for you to chew on. If you could implement just one new metric, or maybe one architectural fitness function in your current project right now, which single one do you think would have the biggest impact? Which one would best reveal your system's true health and guide where it needs to go next? That's a great question to ponder.
Definitely something to think about. Until next time, keep learning, keep building, and keep making those informed decisions.